everyone, it's Jasmine Tramell, and I'm going to be your chemistry teacher for a few minutes. I'm going to break down 4 important topics: chemical nomenclature, moles, Avogadro's number, and molar mass. Okay, so chemical nomenclature is basically the naming system chemists use to identify compounds. Every chemical has a unique name, kind of like how every person has a first and last name, so no one gets mixed up. There are 2 main types of compounds. One, there's ionic compounds, where a metal bonds with a nonmetal, and 2 is the molecular compounds, where 2 nonmetals share electrons. Let's start with binary ionic compounds, which are just 2 elements. Binary ionic compounds are made of a metal and a nonmetal. The metal loses electrons and the nonmetal gains them to form a stable compound. In our first example, we're going to talk about lithium bromine. Lithium is a metal and it has 1 valence electron, and bromine is a nonmetal and it has 7 valence electrons. Lithium transfers its 1 electron to bromine and makes lithium stable with its no valence electrons and bromine stable with a full outer shell. Once lithium gives its electron to bromine, it becomes positive, and bromine becomes negative because it gained an electron and this lost an electron. When lithium loses an electron, it now has 1 more proton than electrons, so it becomes positively charged. Bromine gains that electron, now having 1 more electron than proton, so it becomes negatively charged. The opposite charges attract, forming an ionic bond and creating lithium bromine. For example 2, we're going to talk about aluminum oxide. Here we have aluminum and oxygen forming an ionic compound. Aluminum is a metal with 3 valence electrons, so it loses all 3 to form aluminum 3 positive. Oxygen is a nonmetal with 6 valence electrons, so it needs 2 more to fill its shell, becoming O2 negative. To balance the charges, we need 2 aluminum atoms and 3 oxygen atoms. Here's a better representation to show that now we have 2 aluminum ions, which each have a positive 3 charge, and 3 oxide ions, which have a negative 2 charge. The total positive charge is +6, and the total negative charge is -6, so the compound is neutral. When you bring the 2 ions together, 2 aluminum 3 positive charges plus 3 oxygen 2 negative charges becomes aluminum 2O3, also known as aluminum oxide. Next up, we have transition metal compounds. Transition metals can have more than 1 possible charge, so we use Roman numerals in their names. For example, we have copper chloride and copper chloride 2. They're named as copper 1 chloride and copper 2 chloride for the Roman numerals in parentheses. The Roman numerals is what tells us the charge of that metal. Then we have polyatomic ionic compounds, which include ions made up of multiple atoms. For example 1, we're going to use sodium nitrate. Here, sodium is our metal forming a positive ion, the cation. The nitrate ion, NO3 negative, is a polyatomic ion made of nitrogen and oxygen atoms, but together they carry a single negative charge. Since sodium has 1 plus charge and nitrate has 1 negative charge, they combine in a 1:1 ratio to make a neutral compound, sodium nitrate, or NaNO3. For example 2, we're going to do calcium carbonate. Calcium forms a positive 2 ion, and carbonate is a polyatomic ion with a negative 2 charge. When they combine, one of each balances perfectly to form calcium carbonate. We always want to name the positive ion first, then the negative ion, even if the -1 is polyatomic. Next up are moles. A mole is a unit that helps us count really tiny things like atoms and molecules. 1 mole equals 6.022 times 10 to the 23rd in particles, which is the Avogadro's number, but we'll get to that soon. Chemists use moles because atoms are way too small to count individually, so the mole gives us a bridge between the microscopic world and the grams we can actually measure. For example, if 1 mole of carbon weighs 12 grams, then 2 moles would weigh 24 grams. If we do a quick conversion, and let's say I have 9 grams of water, and water's molar mass is 18 grams per mole, to find how many moles of water, we're going to convert grams of water into moles of water using the molar mass. Molar mass tells us how many grams are in 1 mole of a substance. So in our given, we have 9 grams of H2O, water. And we also have a molar mass of 18 grams per mole. We write 9 grams of water, then multiply by the conversion factor, 1 mole of water per 18 grams of water. This helps us cancel out the grams and end up with moles. Now we want to cross out the grams and so that we only have moles left. Now we're just going to divide 9 by 18 and we get 0.5. That means we have half a mole of water. Now we can take it one step further and convert moles to molecules using Avogadro's number, 6.022 times 10 to the 23rd molecules in 1 mole. Half of that is about 3.01 times 10 to the 23rd molecules of water. Therefore, 0.5 moles of water equals 3.01 times 10 to the 23rd molecules. Alright, now let's talk more about Avogadro's number, 6.022 times 10 to the 23rd. This number tells us how many particles are in 1 mole of any substance, atoms, molecules, or ions. This number connects atoms, molecules, and moles by serving as a bridge between a tiny scale of individual particles and the measurable amounts we use in chemistry. For example, just as a dozen means 12 atoms, a mole means 6.022 times 10 to the 23rd particles. So 1 mole of carbon atoms contains 6.022 times 10 to the 23rd carbon atoms, and 1 mole of water molecules contains 6.022 times 10 to the 23rd water molecules. For example, let's say I have 2 moles of oxygen atoms and I need to find how many atoms that is. I know that 1 mole equals 6.022 times 10 to the 23rd atoms, which is Avogadro's number. So to find out how many atoms I have in 2 moles, I would just multiply 2 by Avogadro's number. Or in formula, it would look like this. And this would equal 1.204 times 10 to the 24 atoms of oxygen. Avogadro's number is unimaginably large. If you had 6.022 times 10 to the 23rd grains of sand, they would cover the entire Earth, including oceans, in a layer of several miles deep. This helps explain how much of 1 mole really is. Now let's finish with molar mass. This one connects everything we just talked about. Molar mass is the mass of 1 mole of a substance. It tells us how many grams are in 1 mole of atoms, molecules, molecules, or ions. You can find the molar mass of any element by looking at the atomic mass on the periodic table. That number in atomic mass units is the same number as the molar mass in grams per mole. To find the molar mass of a compound, you just add up all the molar masses of all the atoms in its formula. For example, calcium chloride. Calcium has a molar mass of 40.08 and chlorine has a molar mass of 35.45 grams per mole. And there are two of them, two chlorides, so we just multiply times 2. And that'll give us 70.90 grams per mole. Now we just add up the two numbers and we get 110.98 grams per mole. So the molar mass of calcium chloride is 110.98 grams per mole. Now if we're converting moles to grams, for example, if I have 0.50 moles of calcium chloride, I multiply by the molar mass. Therefore, if I multiply 0.50 times 110.98 grams per mole, I would get 55.49 grams. That means 0.50 moles of calcium chloride has a mass of 55.49 grams.